Okay team, here we're gonna look at Quicksort one more time. We're gonna look at a best case scenario and then a worst case scenario. So I'm gonna pick index 0 as my pivot. I'm gonna put my hypothesis, my turtle to represent my hypothesis of the one after where I think the pivot is gonna be. And then my duck is gonna walk through. So I start the duck and the turtle both at index 1. And if this thing is smaller than the value at the pivot, which it is, then I actually swap whatever's at the turtle and the duck, but they're pointing at the same thing or referencing the same thing. So we don't have anything to do, but both the duck and the turtle will increment. Again, they're the same, so I would swap and the duck and the turtle increment. Okay, now something is bigger, so I'm not gonna move the turtle. I update the duck. The duck is referencing something that is smaller than the pivot, so I swap the element at the duck's location and the turtle's location, and I increment the turtle. Similarly, the duck keeps walking along, not smaller than the pivot, not smaller than the pivot, not smaller than the pivot, smaller than the pivot. So now we're gonna swap the elements, and then we update the turtle to one more. So now my hypothesis is that the pivot goes here. My duck keeps walking through, it finds one more element that's smaller. I swap it with the spot at the turtle is incremented, and then the duck again goes to the end, and now I'm done with the duck. Then what happens is, this is my hypothesis of where the pivot is. It's one after where I have the hypothesis that the pivot is. And that is actually the correct spot for the pivot to be. So I do one last sort that puts that 30 exactly in the right spot. So that 30 is essentially done. And then what I'm gonna do is I'm gonna call Quicksort with this subset of the array and Quicksort with this subset of the array. And I'm gonna walk us through what that will be. So we'll try and do it a little bit more quickly. They both start off here. Swap if it's smaller, it is. Swap if it's smaller, it is. And then it's bigger. So we're good. Then my hypothesis is that this is the pivot. It's one before the turtle. And so I swap what I chose as my pivot. And now that 15 is in exactly the right spot. And I'm able to make recursive calls with that subset of the array and this subset of the array. And we can have a base case where if there's just two elements, we just sort them. So we go like, whoop, yeah. It's not worth the whole rigmarole of Quicksort if there's just a few elements. So now actually the first half of the array is sorted. I can also make a recursive call on this subset of the array. So my pivot will be 45. I start my turtle at 49 and I start my duck at 49 at whatever index 49 is at. I'm looking for something smaller. It's not. I find 40 is smaller, so I swap the values at the turtle and the duck, and then I increment the turtle. I'm looking for something smaller. I find it at that 39. I swap them. The duck is done. It's gone through the whole array. And now I find that my pivot should, oh, sorry, I didn't update that one. My pivot should go one before the turtle. So I move my pivot into place. And now that pivot is in exactly the right spot. And then I am just recursively calling Quicksort on a 2-element array, so I can just check that they're sorted. Similarly, a 2-element array, and I can just sort those. And then I was able to sort everything here. And actually, if we look at sort of how it happened, we had kind of a tree-based structure. Okay, it is really just one array, but you can see that like this recursive call that where it chose 30 as the pivot made 2 recursive calls, one where 15 was the pivot and one where 45 was the pivot. Each of them made 2 recursive calls where the whole subarray was just these 2 elements, where the whole subarray was just these 2 elements. And so at every step, we were able to break the problem exactly in half. And that is beautiful. Those are perfectly chosen, carefully constructed pivots that we're working with. Let's look at a case where it does not go like that, where we're able to divide things exactly in half. Okay, you can see here my array is sorted. This is not going to be great for us. So I'm going to start my turtle here. Here's my hypothesis, is that actually the pivot, which I'm selecting as the 0 index, that's where it should go. And then my duck is going to walk through trying to look for items that are smaller than the pivot and goes boop, 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 boop. Nothing smaller than the pivot. So now that 1 is in the correct spot. Okay, that's not really great because I can make a recursive call on this subset of the array, but like I really wanted to break this problem into in half. Like that's where I got a lot of bang for my buck. But that didn't happen. I will use a little peg to say we're done with that one. Now I'm having my pivot be this 2. That's sort of the first element in my subset of the array. I set my turtle there. My hypothesis is that the pivot goes 1 before that turtle. And then I'm looking for evidence that that's false. So I'm looking to find something that's smaller than the pivot. Boop, 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 boop. You can see I found nothing. So now that 2 is in the right spot. And I need to sort this subset of the array. And again, you're like, Colleen, I wanted to split it in half and I didn't get to split it in half. That's bad. I'm going to pick the pivot 3. Hypothesis is there. My duck has to walk through all those elements. It didn't find anything smaller. So the 3 must be in the right spot. But now I just have to make a recursive call that's only 1 smaller. And I wanted it to be half as big. So we're going to keep, can you imagine that we're going to keep going through that? For 4, boop, 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 boop. For 5, boop, boop, boop. For 6, boop, boop. For 7, boop. And every time we wish that we chose a pivot that would split it in half, but we didn't, and we ended up only making the problem 1 smaller. It's good that we at least made the problem 1 smaller, because otherwise our recursion wouldn't work. But we didn't get that same splitting like we got in merge sort that was so powerful for us to be able to solve the problem more quickly than O of n squared. So here, if I choose a pivot where it actually doesn't divide the problem in half, it just removes 1 element from consideration, the runtime is still just O of n squared. And you can imagine that because I have to do 8 steps, and then 7 steps, and then 6 steps, and then 5 steps, and then 4 steps, and then 3 steps, and then 2 steps, and then 1 step. And that is n squared. In computer science, it's going to be super common for us to see some series. So I'm going to see the series 1 plus 2 plus 3 plus 4 plus ... plus n minus 1 plus n. That's going to be super common. And we could look at that as like 1 plus 2 plus 3 plus 4 plus 5. And I can think about them as like these little blocks that I'm totaling up. And then I could just count them, you know, sort of line them up end to end and count them. Okay, but I can also look at this and line them up in a different way. Here, check it out, I've got all the same blocks. But as I line them up like this, I can see they sort of make a triangle. And the height of that triangle, here my biggest block is the 7 block. So the height of that triangle is 7, because I have 7 terms. And then the width of my block of my triangle is also 7. But it's a little tricky because it's not just 7 times 7 divided by 2, because they kind of go over the middle line. But check it out. Check it out, we can fill in that gap with these black boxes. So the height is still going to be 7, but now I've added 1 more to the width. So instead of being 7 wide, it's going to be 8 wide. And in general, this could have a height of n and then a width of n plus 1. And now literally it's half the blocks. And so the sum from 1 to n is just going to be n, the height, times the width, n plus 1, and then it's half of those blocks. So the sum of this 1 plus 2 plus 3 plus 4 up to n is just n times n plus 1 over 2. So if we weren't able to divide our array when we made 2 calls to Quicksort, if the pivot was a really bad pivot that didn't split it in half, we might end up doing n steps, and then n minus 1 steps, and then n minus 2 steps, and then n minus 3 steps, all the way down to 1. So an O of n squared operation. In that case where our pivot actually didn't divide our array, or like the subset of the array that we were trying to sort anymore, it really just removed 1 element. So that was, in our worst case scenario, Quicksort was going to be O of n squared. But here, if Quicksort divides the array in half each time, actually the big O runtime is O of n times log base 2 of n. So in the best case scenario, it's just like merge sort, where every time we were able to split it in half each time. And just as a reminder, log base 2 of x is the power you need to raise 2 by in order to get to x. And so it's really just the inverse of exponentiation, even though I think it looks a little bit weird and funny.